Our series of revision for candidates. I welcome you to our today's topic, which is matrices. I'm your teacher Elphas Ndenga, and I hope we will be able to enjoy the lesson. Welcome. Now, we want to look at what the whole topic is about, and in summary, our today's lesson is going to cover four main areas. These are the objectives of our today's lesson. Number one, we will look at the determinant of 2 by 2 matrix. We will be able to look at the inverse of a 2 by 2 matrix, and then look at the singular matrices, and then finally we'll be able to look at solutions of simultaneous linear equations using matrices. And so even before we look at the determinant of a 2 by 2 matrix, I want students to be able to remember one thing about matrices, because determinant comes towards the end of the topic, and so it is important you understand the basis on which determinant is about. Before we look at determinant, then we need to understand what is a matrix and what constitutes to a matrix. And so when you're looking at the determinant, we can be able to tell exactly what the topic or the determinant is about. So when we talk about the matrix, when we talk about the determinant, simply a matrix, we are referring to the arrangement of elements. We are referring to the arrangement of elements in rows and columns. For example, we can have a matrix with element A, B, C, and D. This is a matrix, and A, B, C, and D are what we call the elements. So a matrix is made up of three things. One, it is made of elements, and elements are simply numbers that form a matrix. For example, a matrix that we've given A, B, C, D, the elements are A, B, C, and D. Now, the elements in a matrix are arranged in either rows or columns. When we talk about the rows, we are talking about the horizontal arrangement. Like in this case, A and B are in a row, C and D are in a row again. So it means this matrix has two rows. When we talk of columns, we talk about the vertical arrangement. So in this case now, this will be a column. Again, this will be a column. So columns are vertical, while rows are horizontal. That is good to understand in matrices. Number two, you will need to understand again that a matrix has elements arranged in diagonals. Remember, the understanding or the foundation of matrices is simply the rectangular arrangement of elements. So they are arranged in what we call diagonals. And we have two diagonals in a matrix. For example, I will write again, these are a matrix A, B, C, D. In this matrix, A and D are in one diagonal. So this is the first diagonal of a matrix, and this diagonal, we call it the leading diagonal. This one is called the leading diagonal, or the main diagonal. And then if you look at the elements C and B, the elements C and B, in this case, are in what we call the other diagonal. They constitute what we call the other diagonal. And so we have two diagonals, the leading diagonal and the other diagonal. So that now, from there, we can now be able to understand how to determine the determinant of a 2 by 2 matrix. And this 2 by 2 is actually what we call the order of a matrix. And the order of a matrix is simply defined by the number of rows against the number of columns. Count the number of rows in a matrix, and then count the number of columns. We'll be able to get the order. And that is why now, in our today's lesson, we want to analyze the determinant of a 2 by 2 matrix. Simply, the order of the matrices that we want to look at, their determinant is the 2 by 2 matrix. So how do we determine the determinant? In short, we are saying that the determinant is simply the difference of products of elements in the leading diagonal, the products of elements in the leading diagonal, and the products of elements in the other diagonal. So meaning, as I've shown you before, the leading diagonal and the other diagonal, we are going to get the products of elements in the leading diagonal. We subtract the products of elements in the other diagonal. In this case, for example, in a general case where we have a matrix A with the elements A, B, C, and D, as you can see, the determinant of this matrix will be, now the elements in the leading diagonal is A and D. The elements in the other diagonal now is B and C. So we get the product of A times C, then minus B times D, that is B times C. That becomes the determinant of our matrix. And so when we are looking at this case, for example, if we have, what you are meaning is we have the elements A, B, C, and D to bring it now practically. We've said that A and B, this is the leading diagonal. As I've indicated, this is the leading diagonal. And then this C and B are in the other diagonal. And so the determinant, you're saying, take the product of elements in the leading diagonal, that is A times D, we minus the product of elements in the other diagonal, that is C times B, and that gives us BC. And this A, B, and C are simply variables that could mean any number. It could represent any number. And so do not get scared when I'm using A and B, C, and D in this case. They are only used to represent numbers that we shall be able to look at in our examples. So good. Therefore, the main point that you should have noted, students, is that the determinant of a matrix is simply the difference between the products of elements in the leading diagonal by the products of elements in the other diagonal. Multiply the elements in the leading diagonal, subtract the products of elements in the other diagonal. What you get is what we call the determinant of the matrix. So let's look at an example and see. Now, this is our question. We are told to determine the determinant of each of the following matrices. We are told to determine the determinant of each of the following matrices. And the matrices that we have negative 1, we have negative 1, 8, 7, 6. We have part A. We have a matrix which is 3, 6, 3, 6, 5, 2, 3, 6, 5, 2. We need to determine the determinant of this matrix. We've said that product of elements, so we shall then be able to solve this and say our solution will be the elements in the leading diagonal. It is 3 and 2. So we'll say our determinant is equals to 3 times 2, 3 times 2. And then the other diagonal has the elements 6 and 5. So we subtract 5 times 6. We subtract 5 times 6. When you multiply 2 by 3, you get the solution is 6, minus 5 times 6 gives us 30. And so the difference here gives us negative 24. And that is the determinant of our matrix. So we've been able to see that is simply get the product of elements in the leading diagonal by the products of, then subtract the products of elements in the other diagonal. In our second case, students, let's look at this negative 1, 8, 7, 6. Negative 1, 8, 7, 6. In this case, then, we will be able to get our determinant in this case. The elements in the leading diagonal, negative 1 times 6. That is negative 1 times 6. And then we minus 7 times 8. 7 times 8. We minus 7 times 8. So students, if you be able to follow this, what is negative 1 times 6? Negative 1 times 6 gives us negative 6. Gives us negative 6. Minus 7 times 56. That should give us 56. And so then, it means therefore our determinant is negative 62. Negative 62. Therefore, that is simply how we work out the determinants of 2 by 2 matrix. And remember, we are emphasizing it is strictly 2 by 2 matrix, not 3 by 3, not any other order of a matrix for the case of your syllabus. So we look at the next item, which is the inverse of a matrix. The inverse of a matrix. What is the inverse of a matrix? And in this case, again, we are looking at the inverse of a 2 by 2 matrix. Now, if you get a matrix, for example, P, and another matrix Q, when we have their products giving us an identity matrix I, and identity matrix for a 2 by 2 matrix is simply 1, 0, 0, 1. So in that case, we say P and Q are the inverse of each other. In other words, if you take a matrix, multiply by its inverse, then the solution will be the identity matrix. And the identity matrix of a 2 by 2 matrix is known. It is simply a matrix with the elements 1, 0, 0, 1. So let's see in details what is the inverse of a 2 by 2 matrix and how do we work out the inverse. In this case, we are saying that the inverse, if P and Q are matrices, and that P, Q, meaning the product of P and Q, is equals to I. If you multiply P, Q, you get I, where I is an identity matrix. Then Q and P are inverse of each other. P and Q are the inverse of each other. And so when we look at this, we'll be able to see that when we are determining the inverse of a 2 by 2 matrix, how do we determine the inverse of a 2 by 2 matrix? The procedure is very simple. When you're determining the inverse of a 2 by 2 matrix, the first thing that you must do is find the determinant. And so that is why it was important for us to understand what is the determinant of a 2 by 2 matrix. Because in it, from there then, we'll be able to get the inverse. So the first step that you do is you determine the determinant of the matrix. Once you've determined the determinant of the matrix, step number 2, you are supposed to interchange the elements in the leading diagonal. And then once you've interchanged the elements in the leading diagonal, step number 3, you reverse the signs of elements in the other diagonal. Now when you reverse the signs, if it was negative, it becomes positive. And if it was positive, it then becomes negative. Then finally, you take the resulting matrix, you divide by the determinant. You take the resulting matrix, then divide by the determinant. So this is what I simply mean in this case. If we have a matrix, if we have a general matrix, AB, we shall still use our matrix A, B, C, and D. In this case, if we are determining the inverse, we are saying step 1, get the determinant. And so what will be the determinant in this case? We've said the determinant is equals to the products of elements in the leading diagonal, A and D, that is A, D, minus the product of elements in the other diagonal, C and B. That gives us CB or BC. That is our determinant. Now, for this case, I want us to say or to refer to this one as our determinant A. Let's call it our det A, meaning the determinant of our matrix. Then step number 2, we are saying interchange the elements in the leading diagonal. Now, A and D are the elements in the leading diagonal. We interchange, meaning where there is A, put D. And when there is D, put A. And so I will have D, A in this case. Then you reverse the sign of elements in the other diagonal. B and C are the elements in the other diagonal. Change their signs. So this becomes negative, this becomes negative. And so we have negative B, and negative C. And then this is the matrix we are now obtaining from that arrangement. And so this matrix, we divide it by the determinant. Dividing by the determinant simply means I will take 1 over the determinant, then I multiply by the matrix. If you do that, students, you will have determined the inverse of the matrix. So it is very simple. Only follow the three procedure. Number one, get the determinant. Number two, reverse the elements in the leading diagonal. Then the same number two, after reversing the elements, you change the sign or reverse the signs of the elements in the other diagonal, and then you divide by the determinant. Let's do it practically. So let's follow the example and see what we have. In our question, you're told, show that M, which is 7, 4, 5, 3, and N, which is 3, negative 4, 5, 7, are inverse of each other. Are inverse of each other. M and N, we need to confirm that they are indeed the inverse of each other. And remember, in the description of an inverse matrix, I've pointed out that if two matrices are inverse of each other, the product of those matrices will give us an identity matrix. So in other words, we simply want to see, if we multiply these matrices, are we going to obtain an identity matrix? That is what we have now as our task number one. So let's see how we'll be able to determine in this case. We'll take our matrix, which is 7, that is 7, 4, 5, 3, and then we multiply by 3, negative 4, negative 5, 7. Again, students, remember, you worked out multiplication of matrices. So in this case, we are going to multiply these two matrices because they are compatible. M and N are compatible. The reason being they are of the same order. Remember, we look at the compatibility looking at the order of the matrix and then the number of rows and columns from each of the matrix. That will be able to help us determine whether the matrices are compatible or not. But in this case, since they are all 2 by 2, then definitely they are compatible matrices. So let's look at how do we multiply. The procedure is we multiply the row by the column. Row by the column. That is the order of multiplication of matrices. So in this case, I'll take 7 times 3. That gives us 21. 7 times 3 gives us 21. Then 4 times 5, negative 5 gives us negative 20. Negative 20. Again, the other side, 7 times negative 4, it will give us negative 28. Negative 28. Then 4 times 7, that gives us positive 28. Positive 28. Again, 5 times 3 gives us 15. Gives us 15. And then we have minus 3 times negative 5, that is negative 15. And then the other side, 5 times negative 4, that gives us negative 20. Negative 20. And then 3 times 7, that gives us 21. So we add 21. That is now our product. And so when you work out 21 minus 20, it will give you 1. If you work out negative 28 plus 28 is 0. 15 minus 15 is 0. And negative 20 plus 21 is 1. And therefore, it means, therefore, in this case, the matrix is 1, 0, 0, 1. And since this is an identity matrix of a 2 by 2, then it means, therefore, M and N are inverse of each other. It means, therefore, that M and N are inverse of each other, because that was the task that we were to be able to confirm whether M and N are inverse of each other. And we are concluding, yes, indeed, that M and N are inverse of each other. The reason being the product of M and N is an identity matrix, which is 1, 0, 0, 1. Therefore, students, I hope by that, so far, you are following and you are able to understand what we are talking about, the inverse of matrix. Again, this is the procedure that I've highlighted before. If you want to determine the inverse of a 2 by 2 matrix, we said number 1, you find the determinant of the matrix. And we are saying determinant is simply multiply elements in the leading diagonal by the product of elements in the other diagonal. Then you subtract, you get the determinant. Step number 2, you reverse the signs of elements in the other diagonal. Reversing the signs means if it is a sign assigned to the element is negative, it then turns to be positive. If it is positive, it turns to be negative. That is what we do in step 2. You reverse the sign of elements in the other diagonal. Step number 3, after you've reversed the elements, which is not there, number 4, you simply divide the matrix by the determinant of the matrix. You divide the matrix by its determinant. Good. So let's then look at the following questions and see how we work out the determinant of these matrices. The inverse of the matrix 3, -2, 7, and 5. We want to work out the inverse of the matrix 3, -2, 7, and 5. So we will work out and see. In this case, we have if we work out the determinant of this matrix, the determinant of this matrix will be the determinant of this matrix. The determinant of this matrix will be, we take the products of elements in the leading diagonal. We have the determinant, which is the product of elements in the leading diagonal. Determinant is equals to, and our elements in the leading diagonal is 3 and 5. So we'll have 3 times 5. And then we minus the products of elements in the other diagonal, which is now 7 by -2. So we write 7 times -2. And so this gives us 15. 15 minus 14. Why minus? If you take 7 times -2 gives us -14. And so we have 2 minus after each other. That becomes now a positive. And so the resulting solution here becomes 29. That is the determinant. Again, students, if you have the determinant, what is the next step from the procedure we've highlighted? Yes, we've said that the next step is to interchange the elements in the leading diagonal. And so let's see how do we interchange the elements in the leading diagonal. Now we have 3 and 5 as the elements in the leading diagonal. When you interchange, it means 3 will take the position of 5, and 5 takes the position of 3. And so we will have 5 in that position, then 3 in the position of 5. Then after that, change the sign of these elements. That is 2, -2, and 7. In this case, this is negative. If you change the sign, it becomes +2. And so the element there now becomes 2. And if change the sign of 7, we have -7. So this is now our resulting matrix. This is our new matrix, which we divide by the determinant. So we take 1 over the determinant, which is 29. 1 over 29. And so by expansion, we obtain then the inverse by simply expanding. You expand, simply multiply 1 over 29 by every element in the matrix. And if you carry out the expansion, this is what will happen. So let's expand together. We have 1 over 29 times 5. That gives us 5 over 29. 5 over 29. And then we have 1 over 29 by 2. That gives us 2 over 29. 1 over 29 by negative 7 gives us negative 7 over 29. And then lastly, 1 over 29 by 3 gives us 3 over 29. 3 over 29. Therefore, this is our inverse. That is our inverse, which is 5 over 29, 3 over 29, and then that is 2 over 29, negative 7 over 29, and 3 over 29 as our inverse of the matrix. And so that is what we do when you are looking at the inverse of a 2 by 2 matrix. Simply remember the procedure. Number 1, obtain the determinant. Number 2, reverse the elements in the leading diagonal. Number 3, change the signs of elements in the other diagonal. And then now when you have that matrix, you divide it by the determinant of the matrix. Good. So let's look at another case again. Let's look at another case. The case that I want us to be able to look at is if, for example, we are told now to determine the inverse of the matrix, which is 4, 3, 1, negative 3. We want to obtain the inverse of this matrix. 4, 3, 1, negative 3. The solution again will be the same. We'll solve as follows. We will take first step, the determinant. So we'll say the determinant is equals to, we take 4 times negative 3, then we minus 1 times 3. Minus 1 times 3. From your calculators, what is 4 times negative 3? The value is negative 12. So we have negative 12 minus 1 times 3, that is 3. And so the solution is negative 15. That is our determinant. Then number 2, we are saying reverse the elements. Now we have 4 and negative 3. These are the elements in the leading diagonal. So we interchange them. We don't change their sign, but we interchange these elements. So where there is positive 4, write negative 3. So I'll have negative 3. And then where there is negative 3, write 4. So I'll write 4. Then change the sign now of these two elements which are in the other diagonal. Now its name is simply the other diagonal. So don't ask what is the name of the other diagonal. It is called the other diagonal. So you change the sign. Now where there is 3, now becomes negative 3. This becomes negative 1. So we'll write it here and write negative 3, negative 3, negative 1. So that is now our resulting matrix. Then we've said you then take this matrix and simply divide by 1 over the determinant. So in this case, it is 1 over 15. And remember, this is negative, so we have negative 1 over 15. If we expand this one again, we are going to obtain a matrix. Negative 1 over 15 times 3 gives us 3 over 15. If you simplify that, you'll get 1 over 5. Then negative 1 over 15 times 3 again, that is now giving us again 1 over 5. 1 over 5. Then the other side, this becomes 1 over 15. 1 over 15. And the other one becomes 4 over 15. That is negative 4 over 15. So this becomes the inverse of our matrix. That is the inverse of our matrix. So I believe our students are following this, and you can be able to see what we've been able to do in relation to the inverse of a matrix. So in our final part of this topic, we need now to apply matrices to solutions of simultaneous linear equations. So I will be able to ask, how many know how to solve a pair of simultaneous linear equations? How many knows how to solve a pair of simultaneous linear equations? Because this is captured in Form 1, and in Form 1, we look at solutions of simultaneous linear equations using 3 methods. How many remember the methods? Because now, once you are in Form, this is covered in Form 3. It means you have 2 years back, and that should be able to be remembered when you are looking at this topic as well. We solve by 3 methods. Number 1, we solve using elimination method. Number 2, we can use substitution method. And then number 3, we use graphical method. That is how we solve pairs of simultaneous linear equations in Form 1. And so when you're looking at matrices again, we are adding you the 4th method of solving pairs of simultaneous linear equations. And this is by use of the matrix method. It is very simple, just as elimination, just as substitution, and just as solutions by graphical method. So how do we move in the solutions of simultaneous linear equations using matrix method? The first thing that you must be able to know is that we are going to be given the pairs. That's the pair of a simultaneous equation in terms of x and y, or a, b, or any other letter that can be used to represent the variables that we shall be discussing. So what you must obtain from that, number 1, obtain what you call the matrix equation. The matrix equation simply comes from the equations given. Be able to eliminate the numbers, that is the coefficients of the unknowns, and then write the unknowns as a matrix again, and then the solutions of each equation also will be written as a matrix. And so we are going to form the matrix equation. That is step number 1. Step number 2, we will have to obtain the inverse of the matrix. You obtain the inverse of the matrix. And I've shown you how do we obtain the inverse of a matrix. And lucky enough, we are going to deal with the 2 by 2 matrix, which we've already covered in our lesson, and which is actually captured in your syllabus. Then once you've been able to get the inverse of the matrix, you will be able now to look at, you'll be able to pre-multiply the inverse matrix. You pre-multiply, the matrix equation by the inverse. And pre here is used because if you do post-multiplication, what will be the effect, students? If you take, instead of taking pre, you do post. What will happen is that you will render those matrices incompatible. Why? Because the number of rows in the first matrix, the number of columns in the first matrix, and the number of rows in the second matrix will not be able to match. And when there is a mismatch of the number of columns in the first matrix by the number of rows in the second matrix, whenever there's a mismatch, then we have, or we make those matrices incompatible. And that is why I told you it is quite important to know that when you are looking at the compatibility of matrices in terms of multiplication, we assess 2 things. Number 1, are they of the same order? They could be of the same order or of different order. If they are of different order, then number 2 you must be able to assess is the number of columns in the first matrix and the number of rows in the second matrix. If what is the number of rows in the first matrix is the same as the number of rows in the second matrix, then those matrices are compatible. So let's look at this in practice and see what we are discussing today. So we have solutions, that is solution of simultaneous linear equations, simultaneous linear equations using matrices. How do we solve a pair of simultaneous linear equation using matrices? And I've given you the procedure. Number one, be able to obtain the matrix equation. And then once you have the matrix equation, get the inverse and then do the pre-multiplication. So we will take an example and see how do we solve a pair of simultaneous linear equation given the matrix method. And so let's be able to explain this procedure using the example. You are told to solve. And then we have 2x plus 5y is equals to 9, and then 3x plus 4y is equals to 6. My students, that is the question. How do we move? I've given you 3 steps for those who've forgotten. Number 1, obtain the matrix equation. Number 2, obtain the inverse. Number 3, pre-multiply the inverse. That is, pre-multiply the matrix equation by the inverse of the matrix. So let's analyze our example using those 3 steps. So number 1, we are saying we obtain our matrix equation. And I'm saying to get the matrix equation, simply segregate the coefficients. This is 2. That is 2. We have 5. Then we have the other side. This is 3. Then this is 4. This matrix is a component of x and y. So we have x and y. Then we equate this one to the other side, the right hand side, where we have 9 and 6. That is our matrix equation. You see how it's simple to obtain the matrix equation. Simply means get the elements from the equations, then separate the unknowns, then the other side on the right hand side also put the matrix which is part of the question. Then number 2, what is the inverse? And the inverse of which matrix? The one that is on the left hand side, which is now 2, 5, 3, and 4. And we are saying again, you cannot get the inverse unless you have the determinant. So let's first determine the determinant. We'll write the determinant of our matrix will be equal to, now we'll take 2 times 4, and then we minus 3 times 5. 2 times 4, we minus 3 times 5. 2 times 4, that is 8, and 3 times 5, that is 15. If you take 8 minus 15, you will get your answer is -7. That is -7. That is our determinant. Then get now the inverse. So how do you get the inverse? We've said interchange these elements. Where there is 2, put 4. And when there is 4, put 2. Then change the signs of these elements. This becomes negative, this becomes negative. So once you do this, then you divide by the determinant, which is -7. So what we are going to have is this case. We will interchange 4 and 2. So we'll have now 4 and 2. Change the sign of 5. So we have -5. Change the sign of 3. We have -3. Then, once we have this, we now divide by -1/7. And this becomes, take this by this, -4/7. -4/7. Then the other one becomes 5/7. That means -1/7 times -5, 5/7. This the other one becomes 3/7. 3/7. And lastly, we have -2/7. And so this is our matrix, the inverse of our matrix. So far, I hope we are fine and we can be able to follow that. That is the inverse. Step number 3, what did we do? We said you pre-multiply now the matrix equation by the inverse. If you have the inverse, then pre-multiplication simply means you put it before the matrix equation. And remember, on both sides, that is the left-hand side and the right-hand side, you do the pre-multiplication. And again, I'm repeating, students, if you happen to do post-multiplication, then that matrix cannot be solved. It will be incompatible. And so you must ensure, underline if possible, pre-multiply the matrix equation by the inverse. So let's do it. We'll take now our inverse, which is now negative 4 over 7, 5 over 7, 3 over 7, negative 3 over 7. This matrix is our inverse. So we pre-multiply this one by the original matrix. And remember, the original matrix, this is the matrix equation that we are pre-multiplying with. So we put the inverse before at this point, and again before on the right-hand side. So we will then proceed and say, now, I'll write our matrix here is now 2, 2, 5, 2, 5, 3, 4. Then, being the product again of x and y, to get, do also pre-multiplication on the right-hand side. So I'll write the inverse, which is negative 4 over 7, 5 over 7, 3 over 7, negative 3 over 7. Pre-multiply this one by the matrix, which is now 9, 6, which is 9, 6. Good. What are you saying now? That we have the inverse and the matrix. That takes us back to where we started from. When we are looking at the inverse, we said if you have the matrix and its inverse, the product is an identity matrix. And so what's the identity matrix of a 2 by 2 matrix? We have already seen it is 1, 0, 0, 1. So that is what we are going to work out on the left-hand side. We'll have 1, 0, 0, 1 as our result. Then now we can only do the multiplication on the right-hand side, then be able to work out for the value for x and y. So let's finish up then. We'll have on this side, this is the inverse of this matrix. And so what we are saying is, once you have the inverse and its matrix, the product is an identity matrix. And in this case, 1, 0, 0, 1. 1, 0, 0, 1. Being the product of x and y, to obtain, so we do the multiplication on the right-hand side. So let's work out, students. Take out your calculators. Negative 4 over 7 times 9. Negative 4 over 7 times 9. Our value is negative 36. Negative 36 over 7. Negative 36 over 7. 5 over 7 times 6. That will give us 30 over 7. We go to the second row. 3 over 7 times 9. That will give us 27 over 7. Then negative 3 over 7 times 6. That will give us negative 18 over 7. So since you have your calculators ready with you, I hope you'll be able to work out this one. Let's work out together. Negative 39 over 7 plus 30 over 7, that is simply negative 9 over 7. And so our value of this side will be negative 9 over 7. We have negative 9 over 7. So let's write it here. That will give us negative 9 over 7. And then if we work out the other side, we have negative 3 over. So let's confirm this multiplication. Negative 4 over 7 times this. This is negative 36. Let's change this one. This one is we have so that becomes negative 36. This is negative 36. Negative 36 over 7. And so if we work out that, will give us negative 6. Yes, negative 6 over 7. Then 27 over 7, we minus 18 over 7. And so let's then work out this one. We'll have, this is, let's have this one. This is negative 6 over 7. Negative 6 over 7. Negative 6 over 7 as our value for x. Then again, I hope students you're working out the value for y. I hope you're working out the value of y. So we have negative 6 over 7 as our solution for the first part. Again, we have 27 over 7 minus 18 over 7. That will give us 27 minus 18. That will give us 9 over 7. Again, cross-check so that we have the right figure. 3 over 7 times 9, that is 27 over 7. Then minus 3 over 7 times 6, that is minus 18 over 7. Minus 18 over 7. So we'll have, that is 27 minus 18, which will be, that is over 7. So we will work out this one. So that is our solution for x, and y. This x, y. So if we work out this, we have the solutions for x, which is our solutions for x and y, which we are saying is negative 6 over 7. Negative 6 over 7. That is xy. Xy is equals to negative 6 over 7 over 9 over 7. And so we write this one to be negative 6 over 7. Then that becomes 1 and 2 over 7. That is our solution. So I hope you've been able to see. It is quite interesting and enjoyable if you understand the procedure that we are following. Again, let's look at another example that you can be given in this case for simultaneous linear equations. And so if you are told to use, that is number 2, you are told to use matrix method to solve. Use the matrix method to solve. We have 4x plus 3y is equals to 18. And then we have 5x minus 2y is equals to 11. Is equals to 11. Now, any student who can be able to try this? Yes, the first step we are saying is you get the matrix equation. Good. So let's get the matrix equation. Our matrix equation is simply we are saying our matrix equation in this case will simply be, we'll take, that is 4, 4, 5, 3 minus 2 x y is equals to 18, 11. That is our matrix equation. Again, who can tell us the second step if we have the matrix equation? Good. We obtain the inverse. So how do we determine the inverse of a matrix? First, get the determinant. Then second, we interchange the elements in the leading diagonal. Change the signs of elements in the other diagonal. And then we get, we divide the resulting matrix by the determinant. Good. So let's follow the procedure as highlighted. We'll get now our determinant. Our determinant of the matrix will be equal to, we have 4 times negative 2, 4 times negative 2, then minus, we minus, the other side we have 5 by 3. And so this gives us negative 8 minus 15, which will give us negative 23. That is negative 23 as our determinant. So that is simply minus 4 times minus 2, which is minus 8. Then we minus 15, that gives us negative 23. Then we have said number 2, we get the inverse. So how do we get our inverse? Our inverse will be, we interchange the elements in the leading diagonal. So we have negative 2 coming the position of 4, and 4 taking the position of negative 2. Then we have changed the signs of elements in the other diagonal, negative 3 and negative 5. Then once we have this, we multiply by 1 over 23. That is negative. Remember, this is 3, not 2. So you expand this one, you'll have 2 over 23, 2 over 23. Then we have 3 over 23. We have 5 over 23. Then this is negative 4 over 23. That is the inverse of our matrix. Good. Once we have the inverse, then who can now tell us the next step? The next step is pre-multiply the matrix equation by the inverse. Pre-multiply the matrix equation by the inverse. And so what is that in practice? Let's see it. Our inverse is 2, so we'll write 2 over 3 over 23. Then we have 3 over 23. We have 5 over 23. Then we have negative 4 over 23. This is our inverse, of which we pre-multiply this inverse by the matrix equation. And our matrix equation, when you talk of the matrix equation, this is what you are calling the matrix equation. So you pre-multiply by this equation, where we put the inverse before this side, and again on the right-hand side before. So let's proceed. So I will then have my values, that is 4. Below it, I have 5. Then I have 3. Then negative 2. Then we have xy to give us the same inverse, that is 2 over 23, 3 over 23, 5 over 23, and then negative 4 over 23. Negative 4 over 23. Then we have the other side, 18 over, that is not over, but 18, 11. So that is what we have, and we've said on the left-hand side, this side, when you multiply these two, you obtain an identity matrix. So we will not waste much time multiplying this, because at the end of the day, it is an identity matrix, and the reason being, this is the inverse of this matrix. And once you have an inverse and its matrix, the product is an identity matrix. So we will say then we'll have 1, 0, 0, 1. 1, 0, 0, 1. That is x, y, to give us now on the other side. Let's multiply and see. 2 over 23 times 18, that should be 36 over 23. Then the other one is 33 over 23. So that is 36. 36 over 23 plus 33 over 23. Again, the other side, we have 5 over 23 times 18. That should be 90 over 23. And then the other side, negative 4 over 23 times 11. It will be negative 44 over 23. So we have 90, that is 90 over 23, then minus 44 over 23. Good. Then let's work out this. When you have an identity matrix by any matrix, then it gives you that matrix. So this is xy. That is xy. And then on the other side, we have 36 plus 33. That should give us 69. Divide by 23, the value should be 3. So you have 3. 90 over 23 minus 44 over 23. 90 minus 44, that should give us 46. 46 divided by 23, it will give you 2. So in this case then, it means that our x is equals to 3 and our y is equals to 2. Y is equals to 2. So for those who have not been able to follow, this is where we started. You can be able to cross-check. We had this as the question, 4x plus 3y is equals to 18. 5x minus 2y is equals to 11. We obtained the matrix equation by simply separating the coefficients of x and y to form the matrix of a 2 by 2. So we got 4, 3, 5, negative 2. And then being the components of x and y to be equal to 18 over 11. Then step 2, we found the determinant. Determinant is 4 times negative 2, negative 8, minus 15, that gives us negative 23. We then obtain the inverse simply by interchanging the elements in the leading diagonal and then change the signs of elements in the other diagonal, multiply by 1 of the determinant, that gives us our inverse. Then lastly, you do the pre-multiplication of the matrix equation by the inverse of the matrix, by the inverse of the matrix. So that is how we solve simultaneous linear equations using matrix method. Finally, students, let's look at a very brief part, which is simply what we call singular matrices. Now, students always ask, if we have a singular matrix, do we also have a plural matrices? We don't have them. We have only singular matrices, and our singular matrix, in understanding as it is in mathematics, is not in terms of what you do in languages. But here, a singular matrix is simply a matrix that has no inverse. This matrix has the determinant who's equal to 0. So if we work out the determinant of any matrix and get the determinant is 0, then the conclusion is that that matrix is a singular matrix. A singular matrix, in short, it is simply that matrix whose determinant is 0, and they have no inverse. They have no inverse. So that is briefly what we shall look at as we finalize our lesson. We have singular matrices. We have singular matrices. Singular matrices. When you're looking at singular matrices, our singular matrices, it's simply a matrix. This is a matrix whose determinant is 0. Whose determinant is 0. And in this case, I'm saying again, they have no inverse. They have no inverse. Good. The determinant is 0 and they have no inverse. As simple as that. So most of the time, this part is very important because questions will come in singular matrices and require your understanding in quadratics. Remember, quadratics is in Form 2 and Form 3. Quadratics, where we will be looking at solutions of quadratic equation, because at the end of the day, you are likely to come up with a quadratic equation. And by now, I understand that you are able to know that we solve quadratic equations using different methods. For example, yes, we have what we call the completing square method. Number 2, factorization method. And number 3, we use the quadratic formula. Those are the 3 methods that we use to solve quadratic equations. So if in any case, given a question on singular matrix, you obtain a quadratic equation, then be able to think very fast of the 3 methods: completing the square method, factorization, and quadratic formula. Then in some cases, you may need also graphical method, but since the question might be 4 marks, you don't need to draw the graph. Only use the 3 methods that we've been able to highlight. So finally, let's look at a very simple case, and then we can be able to wind up our lesson. If you're told, in this case, that you are told to determine the value, our question, you're told that you determine the value of x. Determine the values of x for which m, and m here is a matrix which is defined by 2x, then 1, x squared, 2, for which this matrix has no inverse. For which this matrix has no inverse. Determine the values of x for which the matrix M, 2x, x squared, 2, and 1 has no inverse. Remember, we are saying again, if it has no inverse, the determinant is 0, and definitely that matrix is called a singular matrix. Very fast, let's get the determinant. We'll take 2x by 1, 2x by 1, we minus 2 times x squared. So that will give us 2x, we minus 2x squared, and that should give us 0. And so we factor out 2, x is common. We factor out 2x, then we are left with the 1 minus, then we have x is equals to 0. In this case, then it definitely tells you if 2 numbers, their product is 0, then it means one of the numbers has to be 0. So in this case, then 2x can either be equal to 0, 2x should be equal to 0, in this case implying that this implies that x is 0, or it could be 1 minus x is equals to 0, and this will imply that x equal to 1. That implies that x is equals to 1. Because if you take 1 to the right hand side, it becomes negative. We divide by negative, then get positive 1. So it means the values of x is 0 and 1. Maybe if they change the question and say you write down the possible matrices of M, then it simply means replace in x equivalent to 0 you have 0, this will be 0, and this will remain 2 and 1. That will be one possible matrix, 0, 0, 2, 1. And when x is 1, now replace here with 1. So it will be 2 times 1, which is 2, and 1 squared, which is 1. So the matrix will be 2, 1, 2, 1. Those will be the possible matrices of when replacing in the values of x. So that is what we had to cover today. That is what we had to cover today. We were been able to cover 4 parts. Number 1, I've explained to you how we get the determinant of a 2 by 2 matrix. And we said the determinant is simply get the difference of products of the elements in the leading diagonal by the products of elements in the other diagonal. That is the determinant. And strictly they have to be 2 by 2 matrices. Number 2, we've highlighted how to get the inverse of a 2 by 2 matrix. And we are using 3 steps. Number 1, you get the determinant. Number 2, change the sign of elements in the, that is, interchange the position of elements in the main diagonal or leading diagonal and reverse the sign of elements in the other diagonal. Then you multiply by 1 over the determinant. And number 3, we've looked at what is a singular matrix. And I've said a singular matrix is a matrix whose determinant is 0. And then finally, we've discussed how to solve a simultaneous linear equations using matrices. And in this case, I've given you 3 steps. If you are given simultaneous linear equations, as it is when you are taught in Form 1, what you do, you obtain the matrix equation. Once you've obtained the matrix equation, you now get the inverse of the matrix and pre-multiply the inverse, the matrix equation by the inverse. And then you solve for the values of either x or y or any unknown that you will be given in that case. And that is exactly what I want you to do. But now, as we end up the lesson, I want to leave you with something to be able to think about. A case in application of word equations to simultaneous equation. Because you will be given a statement, then form your own equations and solve using matrices. Such cases are very much common. So do not forget and do not assume that it will always be as direct as we've put it, that you'll be given the simultaneous linear equations to solve using matrices. As sometimes it might not be the case. What will be, we'll give you the statement, then formulate the equations, and then use matrices to work out those equations. So I think that's enough for today. We can end our lesson for now. And I wish you well as you keep on revising. And remember, all is here on KUTV Elimu Live. Have a nice day. Enjoy your rest of the day.